Hello, my dear students. Today in this class we will discuss elementary transformation of a matrix and invertible matrices. So let's start. Number one, elementary operations or transformation of a matrix. There are 6 transformations or operation on a matrix. 3 are row transformation and other 3 are column transformations. These transformations are necessary in order to find out the inverse of a matrix. This will be discussed in the next topic. First, number 1, elementary operation or transformation of a matrix. Number 1, the interchange of any two rows or two columns. The interchange of any two rows or columns. It is denoted by Ri interchange to Rj. That means the ith row interchange with zth rows. Similarly, Ci interchange to Cj. That means the ith column interchange with zth columns. For example, A equal to 2, 3, 5, 6, 7, 8, 9, 10, 11 is a matrix of order 3 by 3. We take an example. A is a matrix of order 3 by 3. If we apply R1 interchange to R2, then we have the resultant matrix will be R1 interchange to R2, then 6, 7, 8, 2, 3, 5, R3 does not change. Therefore, the resultant matrix will be 6, 7, 8, 2, 3, 5, 9, 10. Sorry, this element is 11. The next point. What is the second transformation says? The second transformation says the multiplication of the elements of any row or column by a non-zero number. The multiplication of any row or column by a non-zero number. It is denoted by Ri tends to k into Ri. That means multiplying each element of ith row by non-zero constant number k. Similarly, we can write Ci tends to k into Ci. That means multiplying each elements of ith columns by non-zero constant k. For example, A is a matrix 2, 3, 5, 6. If we apply R1 tends to 3 into R1, then the resultant matrix will be R1 tends to 3 into R1. That means multiplying each elements of first row by 3, and 3 to the 6, 3 to the 9, and R2 does not change 5, 6. This is the resultant matrix. Next, number 3. The addition of the elements, the addition to the elements of any row or column, the corresponding elements of any other row or column multiplied by any non-zero number, and it is denoted by R1 tends to R1 plus k into R2, or C1 tends to C1 plus k into C2. Sorry. Ri tends to Ri plus k into Ri, or Ci tends to Ci plus k into Ca. Ri tends to Ri plus K into Ri. That means addition to the elements of ith row, the corresponding elements of the zth row multiplying by K, then it is denoted by Ri tends to Ri plus K into Rj. Similarly, that means the addition to the element Ci, the corresponding elements, the addition to the elements ith columns, corresponding elements to the zth columns multiplied by K. For example, A equal to 1, 2, 3, 2, 5, 1 and 6, 7, 2. If we apply R1 tends to R1 plus 2 into R2, then we have R1 tends to 2 into R2. R1 tends to R1 plus 2 into R2. That means 1 plus, for 1 elements, R1 1 plus 2 into 2. This is equal to 5. Next, 2 plus 2 into 5. 5 to the 10, 12. Next, 3 plus 2 into 1. This is equal to 5. And the second row and third columns does not change. Therefore, 5, 2, 5, 1, 6, 7, 2. If we apply C1 or C2 tends to C2 plus 3 into C3, then we have C1 does not change, 1, 2, 3, 1, 2, 6, and C2 tends to C2 plus 3 into C3, C2 2 plus 3 into 3, 3 into 3 9, 9 plus 2 11. Next, 3 into 1 3 plus 8 5. Next, 7 plus 2 into 3 6 13, and third column does not change. The resultant matrix will be 1 11 3 2 8 1 6 13 2. Next, we will discuss invertible matrices. Invertible matrices. What is invertible matrices? If A is a square matrix of order m by n, if A be any square matrix, square matrix means the number of rows is equal to number of columns. Square matrix of order m by n, then there exists another square matrix B of the same order m by m, such that AB equal to BA equal to I means arithmetics of order m by m. Then A is called invertible matrices, invertible matrix, and B is called inverse of inverse. It's called inverse matrix. If A, B, N is square matrix of order m, and there exists another square matrix B of the same order m by n, such that AB equal to BA equal to I means arithmetics of the order m by m, then A is called invertible matrix and B is called inverse matrix. For example, let A equal to 3512 and B equal to 2 minus 5 minus 1 3. Let A equal to 3512 and B equal to 2 minus 5 minus 1 3 are two matrices. Let A and B are two matrices. Then AB equal to A into B equal to A equal to 3512 into B equal to 2 minus 5 minus 2 minus 1 3. Then we have for first elements we multiply first row with first column, then 3 into 2 6, 5 into minus 1 minus 5. For second elements we multiply first row second column, 3 into minus 5 minus 15, 5 into 3 plus 15. Next 1 into 2 into minus 1 minus 2. Next 1 into minus 5 minus 5, 2 into 3 6. This is equal to 6 minus 5 1 0 0 1 equal to I 2. I is the arithmetics of order 2. Next B equal to B equal to 2 minus 5 minus 1 3 into A equal to 3 5 1 2 is equal to, for first elements we multiply first row first column, then we have 2 into 3 6 minus 5. Next 2 into 5 10 minus 5 into 2 minus 10. Next minus 1 into 3 minus 3 plus 3, minus 1 into minus 5 plus 6. This is equal to 1 0 0 1. Let A and B are two matrices, then AB is equal to arithmetics of order 2 by 2 and BA equal to, this is the arithmetics of order 2 by 2. Since AB equal to BA equal to I of order 2, then A is called the inverse of the inverse of B. A is called, since AB equal to BA equal to I, therefore A is called the inverse of A A is called the inverse of B. That is, it is written as A is called the inverse of B, and B is also called inverse of A. That is written as this, B equal to A to the power minus 1. Next, we will discuss a theorem. Theorem 1. This theorem is very important. If n be are two invertible matrices, if A and B are two invertible matrices of the same order, then AB whole to the power minus 1 equal to B to the power minus 1 into A to the power minus 1. If A and B are two invertible matrices of the same order, then AB whole to the power minus 1 equal to B to the power minus 1 into A to the power minus 1. These theorems are very important proof. From the definition of the inverse matrix, we can write AB into AB whole to the power minus 1 equal to I, since A into A to the power minus 1 equal to I. From the definition from inverse matrix, we can write AB into A to the power minus 1 equal to I. Now, we multiply both sides by A to the power minus 1. Multiplying A to the power minus 1 by A to the power minus 1 on the both sides. A to the power minus 1 into A, B into AB whole to the power minus 1 equal to A to the power minus 1, since A to the power minus 1 into I equal to A to the power minus 1. Next, A to the power minus 1 into A equal to I into B into AB whole to the power minus 1 equal to A to the power minus 1, since A to the power minus 1 into A equal to I. Next, I into B equal to B into AB whole to the power minus 1 equal to A to the power minus 1. Next, we multiply by B to the power minus 1 on both sides, then we have by B to the power minus 1 implies b to the power minus 1 into b equal to I into ab whole to the power minus 1 equal to b to the power minus 1 into a to the power minus 1. This equal to ab to the power minus 1 equal to b to the power minus 1 into a to the power 1, since I into a equal to a. Hence proof. If A and B are two invertible matrices of the same order, then AB whole to the power minus 1 equal to B to the power minus 1 into A to the power minus 1. Next, we will discuss exercise NCERT exercise 3.4. Before starting this exercise, remember exercise 3.4. Before starting this exercise 3.4, remember, if we want to find a to the power minus 1 using row transformations, this exercise related to elementary transformations of a matrix. Therefore, if we want to find a to the power minus 1 using row transformations, then we write a equal to IA. If we want to find a to the power minus 1 using the rows transformations, then we write a equal to IA and apply a sequence of rows transformations on a equal to IA till we get I equal to B into A. Remember, if we want to find a to the power minus 1 using the row transformations, then write a equal to I and apply a sequence of row transformations on a equal to I till we get I equal to BA. Then B is called the inverse of A. Similarly, if we want to find a to the power minus 1 using columns transformations, then write A equal to AI and apply a sequence of columns transformations on A equal to AI till we get I equal to AB. Then B is called inverse of A. Now we will discuss exercise 3.4, question number 1. Remember this point. Question number 1. 1 minus 1, 2, 3. Find the inverse by using elementary transformations. Find the inverse by using elementary transformations. Let A equal to 1 minus 1, 2, 3. If we want to find A to the power inverse matrix of A by using elementary row transformations, then we write A equal to I. A equal to 1 minus 1, 2, 3 is equal to I is a identity matrix of order 2 by 2 into A. Now we are applying applying R2 tends to, for these elements, R2 minus 2 into R1, then we have 1 minus 1, R2 tends to R2 minus 2 R1, 2 minus 2 into 1, 0. For next elements, 3 minus plus 5, 5 equal to, first row does not change, 1 0. Next, R2 minus 2 into R1, 0 minus 2 into 1, minus 2, 1 into A. Next, this element have to equal to 1, have equal to 1, 0 0, sorry, we applying R2 tends to R2 1 by 5 into R2. Then we have because these elements have to be equal 1 minus 1, this is 0, 1 by 5 into 5 equal to 1 is equal to 1 0 minus 2 by 5 and 1 by 5 into A. Next, applying R1 tends to R1 plus R2, then we have 1 plus 0, 1 minus 1 plus 1, 0, 1, sorry, 1 plus minus 2 by 5, 3 by 5, and 0 plus 1 by 5, 1 by 5. This is equal to minus 2 by 5, 1 by 5 into A. Therefore, inverse matrix of A equal to 3 by 5, 1 by 5, minus 2 by 5, 1 by 5. This is the answer. Inverse matrix of A equal to this. Thank you.